Hello all. I think my little computer, if I recall correctly, is going to struggle big time with this. So I apologise for the fan whirring up later. What are we up to today? Today we are going to have the last look at, well, it's the last look for now, at concurrency via 7 billion humans. There's a couple of levels that I got through when I was doing my first investigation that I thought were really interesting, and I wanted to show you those. Fingers crossed that the stream's coming through okay. It looks a bit dicey to me. You can let me know in the chat if it's not working, and I'll see it later for the VOD. Okay, so we're going not into the game we played before. We're going into my example game, and we'll look at levels I've already done before, but cut out the code I've done and start again. And it's been weeks since I did them, so hopefully I'll forget everything, because that's the point, is to see how we might do this from scratch, not how we might do this. Is that me? Yes, that's me. So it was, yeah, 2022 I thought was super interesting. Let's have a look. 21 and 22. 22 and 23, sorry. So remembering, is there anything new in here? No, these are we've seen all these commands. Let me get rid of my example program. A bunch of random numbers. All workers must pick up the data cube directly in front of them. Only the worker with the highest data cube may remain. All other workers must dive with their cubes into the disposal hole. Okay, so my if statement lets me compare what I'm holding to someone next to me, is the fun new thing here. Let's take a look. Just bear with me a sec. Yeah, so my if statement, remember that this is running on every one of these little workers. So I can look at my own item, and I can look in a direction. So let's say I look right. I've still got the comparison operations just like before, and I can look to see compared to my item, right? I can look left and, or in this case right, and compare that to my item, or I can do it the other way around. So I think that's what I need. Sorry about that. Things going a bit funny on my computer, but I'm back now. So each one's going to have to pick up one of the cells and then look left and right to decide whether they are the ones with the biggest one. So only the worker with the highest data cube may remain. So how can you know if you've got the highest? Because the workers can actually only look left and right. That's the challenge here, I guess. How am I going to do this? Well, I'm certainly going to step forward and pick up an item. Let's do that. Step forward and pick up the item. Now, if the item, I can look at my neighbors, and if I'm bigger than my neighbor, I guess I can stay where I am. And if I'm small, well, if I'm smaller than my neighbor, I know I've got to step forward. So let's everyone look right. Compare that to my item, and if I'm smaller, then I'll work forward. Now I just want to see what this does for me. Okay, so if I run this one, everyone goes steps forward. So those guys all walk forward, because when they looked right, they were smaller. That doesn't work, because we've got the biggest ones walked off, done something wrong. If I look right and that's less than my item, I step forward. No, if it's greater than my item, I step forward. Okay. So this is a good start, right? We've gotten rid of some low ones, but we want to now, it'd be nice to repeat that process again, wouldn't it? So what if So those guys have stepped forwards. I've really forgotten how to do this one. I'm sure there's an easy solution that I'm just not thinking about. I'm going to work my way through it the hard way, but I'm going to feel a bit foolish doing it. Or if I look left and I'm smaller, so that'll definitely help. That'll get rid of some more, because I've got an or statement here. Or if I look left and that's bigger than my item, then I'll also step forward, so that gets rid of more of them. Okay, so now we've got left four quite large ones, and the people on the walls. How are we going to get them to stay? Well, what if I make them step right? Okay, yeah, stop that. If I make the ones who haven't stepped forward step to the right, we're going to get closer. So they're kind of next to each other. If we keep doing that, we might get them all next to each other to go again, right? So if I go back around, so these guys definitely just want to step forward until they jump off the edge. So we can loop them with the jump. It just says keep stepping forward. These guys we can loop back over to here. So if my item or my item then step forwards. So if you've only got blanks left to you, you'll jump down to the else and you'll step right. So I think this will make them all just keep stepping right until we find someone next to them. There we go. Very good. We did it. Okay, so we had to choose which direction we were going based on, ooh, am I close to all the targets? Cool. Your all-time fastest solution averaged 26 seconds. Wow, did much better this time. I came up with a much better answer than my last one, I guess. And I used 8 instead of 14 commands. Okay, so working through it there was better than what I did before. I want to see if I can get one of these. Make it faster. Step, 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 step right, step right. I've got an end statement here, so I guess I can make it run less times by using the end statement. Let's just move on to the next one, shall we? Let's run this again just for fun. Super fast. Go. So what I like about this is that it's showing us how to do an operation that is across the entire array of data, but only looking locally. You're so used to with things like this, saying, well, if I want to find the largest element, I'll look at the first one and I'll remember something, and I'll look at the second one and I'll remember something. I'll remember the maximum I've seen so far, right? But here we can't do that, because each individual process, each individual human can only see left and right of itself. It can't see all the way across. So we have to make local decisions that have the global outcome we want. And I think that's really cool. That's one of the cool things we can do with multi-threaded programs. So there's lots of problems that come up with multi-threaded programs, but one of the advantages perhaps is that we can have tighter algorithms if those algorithms are running in parallel with themselves over and over. So this here is a sorting algorithm, not a sorting algorithm, a selecting algorithm. Selects the biggest element without ever looking at the entire array. Okay. No, I just want to go back to the title screen. I've forgotten how to do that. So there we go. Now let's have a look at the sorting hole. So the next step is to take the same idea but to sort a whole array. Look at this. Arrange the data cubes in order from smallest on the left to the biggest on the right. The data cubes can stay in your work. Let's get rid of this before we ruin ourselves by seeing our answer. Arrange the data cubes in order from the smallest on the left to the biggest on the right. The data cubes can stay in your worker's hands. No need to set them down again. And this is a cool little tip here that I think belies one of the ways that they've dodged some concurrency problems. So if two workers are both trying to walk to the other one's tile, they will swap positions. That's very useful for avoiding deadlock. It's quite easy in a real programming environment for one thread to try and do something and another thread to try and do the opposite, but because they're currently occupying those positions, neither thread can do any. Here they've added a bit of extra logic to say, look, if these guys are trying to do the opposite action, they'll just do it. It'll work because we know they're opposite, so they can swap. That's not generally true in programming languages. So a little shortcut to avoid deadlock there. All right, how might we do this? Well, we got to step forward and pick up. You know, I'm going to try this pick up from in front of me instead. That saves me a step. What are we going to do? We've got to have a local algorithm. The reason these are flashing by the way, is so that I can't see what order I'm going to end up with. Otherwise, I might be tempted to write an algorithm that works just for that order. Here, I've got to write an algorithm that works no matter what numbers come up because I can't even see what they're going to be when I press play. That's why they're randomly flashing by. What the heck these things are, I got no idea. Well, we're going to do the same trick, right? We're just looking locally at what's around us to decide what we should do. Now, thankfully, if we try and move right and the person next to us tries to move left, we'll swap. So that makes things pretty easy. If I just look to my right and see that that person is smaller than me, then I just want to move to the right because I'm obviously bigger and I want to move to the right. Else, well, I could stay still, I guess, if I'm exactly the same, but I could also do I want to move left in the else case? No, I don't want to move left in the else case because remember, I've only just looked to the person to the right. I've just worked out that I'm larger than the person to the right. But that doesn't mean I'm definitely, if I'm not larger than the person to the right, that doesn't mean I'm definitely smaller than the person on the left. That's a different person. I've got to check that one myself. It's a separate check. So if the person to my left is bigger than me, then step left. And I think this covers every single person, right? Because if this person here, yes, it was a lean pocket. What are you talking about? My hobby is, oh, you get to find out things about them. So if lean pocket here looks to their right and sees something larger, then packaging person, when he looks to his left, he will definitely see something smaller. The reciprocals will happen. So she will definitely try and move right. He definitely will try and move left. So they'll get the reciprocal actions and they'll swap. So that avoiding of deadlock thing has been super useful here. There is a challenge that's going to break this right now. I can see it already, which is what happens if I'm equal to the one next to me. I don't do anything. That might be okay. Let's see. So they all pick up and they're all just swapping around. I forgot to jump. Notice we got 2 steps there, not 1, which was interesting because they were waiting until they had a chance to do something. Like this person wanted to step right and couldn't. And anyway, we need to jump. We need to make this loop go round and round. You do that once, that gets you slightly more organized, but we just need to keep doing that until we're completely organized. So you can see a few spots people are spinning their wheels waiting for a chance to move, but eventually they get that chance to move. They're all over the place in different parts of the algorithm now. So notice this, right? This guy here is in that point. Well, we can just click on him over here. This guy's they've all gone out of sync with each other, which is okay because so this guy's sitting here waiting for a chance to step to the left. He knows he has to because she's on 92, but she is not at a point ready to look that direction yet. She's looking left to see if the item's smaller. She'll loop back around and eventually look right to see that she is bigger than this guy, and then she'll try and step right and they'll both swap. But there's this spinning of your wheels stage where the thread or the human or the process, whatever you want to call it, knows what it has to do next but isn't able to do it yet, so it's spinning. Now that's what I mean about the deadlock. If they didn't have this behavior where they'll swap when they're trying to go to the right place, then he's currently deadlocked. He can't move left because she's in that spot. When she finally gets to the spot where she can move right, she'll be deadlocked because he'll be standing in that spot. It's only because they added that functionality that they get away with it. So if you're doing this in a real programming language, well, they wouldn't be swapping physical location, but you'd have to take account of the possibility of deadlock there. So eventually everyone's spinning their Their toes gets a chance to move. I mean, she's the biggest, right? So no, she's not. So we're going to watch her find her place, and everyone finds their place in the end, and we're done. Notice that the algorithm hadn't stopped. There's not actually a way to find out that this algorithm should stop. The little workers can never know that they're in a sorted list. Right? They can't even check right and left and say, oh, well, the one above me is bigger than me and the one below me is smaller than me, because there'll be some stage during the algorithm where that's true, but the rest of the algorithm's not sorted. We could maybe put that in to see what happens. I'm tempted. Let's try that. Yeah, back. Woo, pretty good. Didn't get the... you make this one faster. So let's put that in. Let's say if the left of me is less than me and the right of me is greater than or equal to me, then end. I don't have to do anything else. So I put a stopping condition on. I make the jump go back around so it checks the stopping condition. So that feels like a stopping condition because it means that little person is in the right spot, because as far as they can tell, to the right and to the left is correct for them. Let's see. I sense a problem. No, still going. Maybe it works. I didn't think it was going to work. Yeah, a bunch of threads have ended now. So we can check out them. Vishal 46 has ended. He seems to be in the right place. So we're not finishing here, right? We've still got 2 people running around. We got close, but we didn't get there. So who did we get? We got Aubrey. Well, you're in the right place. You're okay. You can keep going forever. You're in the right place. You can keep going forever. So everyone else has ended. But are we ordered yet? No. We got close, right? 96, 95, 92, 90, 88, 83, 83, 79, 59. There we go. 74's out of place. 61's out of place. Couple are out of place. And what's happened is, at some stage during the process of the algorithm running, these guys have gotten to a place where to the right of them was bigger. I mean, perfect, 61. To the right of him is bigger, 71. To the left of him is smaller, 51. So he just stops. He says, I'm done. But that's not actually his place. His place should be further along here. So you can't put that ending condition in because the local information is not enough to tell you when it's finished. So this is a neat algorithm. Once we get rid of this, it's a neat algorithm in the sense that this is a sorting algorithm. Poof, this tiny little thing here is a sorting algorithm. And boom, off it runs, and it's actually quite efficient too. They all do their thing and finish up where they need to be. Done. Quite an efficient sorting algorithm. It's simpler than any of the sorting algorithms you will have written before, that only works in a multi-threaded environment and only works if you just keep letting the threads run. So lots more to learn, I guess, on that front, but I thought this was a really interesting example to show off. That's all I wanted to show off. There is the next step. Let's do the next one. The next one has the local memory, right? Oh no, the next one's about passing data between threads. All right, I'm going to do one more. Because, excuse me. Oh no, these guys just pass the data directly across. Okay, not so interesting. One of the interesting things I wanted to point out before was that I pointed out before that you can only pass data between threads by dropping a piece of a value somewhere and having another thread look at that value. But they've added to the functionality of the game with a give to, which allows you to actually take a piece of information and pass it on to someone else. In real programming, that doesn't exist. Ultimately, giving something to someone else involves plopping it down in a location and having them pick it up. So I guess this is disguising more than enlightening. We'll leave it there. Plenty of fun things to look at in this game, though. I highly recommend you to play it. I learnt lots of things. I saw lots of things in a different light. Whether you're looking at it before you've learnt concurrency or after you've learnt concurrency, I'm sure you'll find interesting things in there. And it's fun. I quite like these games. As you can see, there are more levels than I can poke a stick at, and I'm really fascinated to see where it ends up. I'll keep working my way through it little by little in between my actual work. Alright. That's all for now.